Okay, good afternoon, everyone. I'm Arshad Bhatt, and today we are presenting on environmental monitoring at nuclear licensed sites on behalf of Tilsit Land Quality. I work in Warrington. I'm a lead consultant for the nuclear technologies team here based in Warrington. The objective of this webinar was to give an overview of how we are working within our team and within our company, and what we have learned in the last few years, and to essentially share that knowledge and experience. So the structure of the presentation is that we discuss the objectives of environmental monitoring programs on nuclear licensed sites. This is not UK specific or Europe specific. It's right across what I have learned over the last 20 years. And what's the environmental monitoring process? What are the challenges in environmental monitoring that I have encountered? What are the two of the finest examples that I can produce, and what are our current capabilities within our company, and what's the vision going forward? So the objectives of environmental monitoring program at nuclear licensed sites within the regulatory context as well as within the commercial context are to complete 100% characterization of conceptual site models and subsurface contamination, and to produce those lines of evidence from the geochemistry of the site, the land drainage, the natural land drainage of the site-built drainage, hydrogeology, and monitoring data. Deliver the site and data connected with the land quality database and its GIS integration. Respond to the requirements of the client regulatory as well as commercial, and to make land assets available for commercial use. And I suppose quite a vital one to gain regulatory confidence, especially in areas of groundwater management and human health risk assessment. So in the next 3 slides, we're going to talk about how environmental monitoring process has been carried out in the traditional approach, and how we have slowly made a shift to a more elaborate and a detailed and a scientific approach. The environmental monitoring process on nuclear sites generally has happened, well, even up to the last 2 years. What we're doing is nuclear installations, fuel-based installations, waste management installations, or reactor activities sites, and you have air emissions, release to ground and surface water, releases to the marine environment, and then we used to be doing your traditional groundwater and surface water and air quality monitoring, dosimetry assessments, human health exposure assessments. Here the key challenges we encountered previously were collection and building the time series data sets, spending a lot of time in characterization and interpretation loops, repeatedly going back to the site, and challenges in data management and visualization, not only from our side, but also on the client side, once the work is delivered to the client. And after that, we had looked at biosphere impacts, ecosystem impacts, and major land use impacts. And finally, we would arrive at what you call an installation baseline position. However, due to the complexity of the geology, complexity of hydrogeology, and some of the queries that have come from the regulatory side, and the change in the industry, that's led us to move towards a more scientific approach. And let me go back to this slide first. Sorry. Yeah, and that's generally been our traditional approach to monitoring. Look at the desk study, carry out the review of the data sets, soil sampling, monitoring, interpretation, go back to the site. But the challenges on the site have led us to change this approach. And I would like to spend a few minutes on this slide. And this is what at the moment is our prevailing practice. And this has come about as in response to challenges from the regulatory side, principally, particularly with respect to delineation of the conceptual site model, with not only with respect to contamination from subsurface contamination from RAD, but also subsurface contamination from chlorinated solvents, subsurface contamination from even solvents and metals. So we at the moment, what we do is we're carrying out, in addition, we carry a detailed site study followed by a gap analysis and building the geology, hydrogeology, and the site drainage maps. Call it a map monograph, and we have all this information available to us before we go towards planning the GI phase and creating the geo-environmental design. And then we go into what we call carrying out the field work. The field work is essentially dictated by all this detailed work, which does take a couple of months to prepare. On an average, before the SGI begins, it takes about 3.5 months to get to that stage. And on field, we do a field examination, strata examination, core inspection, photographs, fracture frequency photographs, quite highlighted that in red because pivotal in building up the conceptual model, and followed by analyses of your samples, particularly soil samples, looking at partitioning and fluxes of the contamination, and getting that vital site-specific K value. And whilst this work is taking place in the background, we also do building the case for numerical hydrogeology, which is the flow and transport model for the site. And monitoring wells are not just what we call old-fashioned wells, but multi-channel monitoring wells. For example, in the UK, the Environment Agency does recommend that. And this is particularly quite useful in capturing the anisotropy of the water-bearing formations, particularly with sites with large concrete covers, because that is influencing, generally large concrete covers are influencing what I call, they create temporary hydrogeological features on site without naming anything specific. And in addition, we have shifted from carrying out 3 rounds of monitoring, but we go for constant monitoring, continuous monitoring now, obviously with the approval of the client, and it's got a significant expenditure from the client side. On the interpretation phase, we focus on building multiple lines of evidence and to build the comprehensive conceptual site model, particularly when you're working on chalk and sandstone aquifers. We are relying on doing some aquifer testing, picking up anomalies on the well using CCTV, and also at the moment we have a situation on one of the cases we are dealing with, the potential use of an NMR on a well. And again, I've highlighted that in red, site drainage and the defect mapping of the site drainage. It's quite pivotal how the concrete spread on the site is changing the natural drainage on the site and impacting subsurface contamination, and can create features that will actually create preferential pathways into the aquifer, and especially when you're working in conjunction with understanding of the fractures. For multiple lines of evidence, we use several techniques that I have picked up from different scientific literatures, regulatory literatures, like the US EPA does it, or one is the keys in building the DQRA, for example, the 14 compartment model for solvents, plume dimension analysis, both lateral and vertical delineation, chemical and isotope speciation. You can use there are several models. Quite a few of them are are freely available. And a vital element of the whole project, which is data management. It's a key challenge. And in this data management, we're shifting towards creating a platform that will give us will provide greater accessibility to data, particularly creating a platform that is what I call a three-dimensional visual and animation platform. So once all this work goes in, then we have essentially a site conceptual model. And this has come about as a result of nearly 2 to 3 years of constant challenging. This change has come about due to constant challenging by the regulator and the commercial requirements of our clients. So if we look at how things were previously and what changes that we have brought about as a result in response to the challenges, the traditional monitoring is quite quickly deployable, and it's not intensive in terms of resource or in scientific methods and the level of scientific interpretation required. It does, however, have very long, I'll say, characterization loops and very gradual progression to remediation. In terms of characterization loops, you're talking about quite a bit of time, 5 years plus, you could be looking at. And in my experience, traditional monitoring does not impact on strategic land use planning in a significant way. However, it is suitable for sites where geology, hydrogeology, site drainage, and contamination profile of the subsurface is not complex. But I must say that that's not quite often the case. The two-suite approach, which we are working on and developing, is what I believe is quite long-term. It's detailed. It's absolutely thorough. It builds multiple lines of evidence, gets the site, substantially improves the data accessibility for the regulator, for us, for our consultant teams, for our clients, and it gives our clients to operate their own data sets. It meets the obviously regulatory requirements. In my experience, it's a significant aid in land management, remediation, optioneering, and infrastructure development. And due to its expenditure that's involved and the resources that are needed to be deployed, I would say it's suitable for commercial sites, large commercial sites, which have some signatures. For example, high solvent use, waste management facilities located near the operational areas, and reactor sites with complex geology. So these are, it's not a comparison, but they are within their brackets. They can be useful. Now, what challenges have I encountered in the last few years, specifically in the last few months? What are the challenges? The key challenges are here, which is what are the challenges of EM at a nuclear license site? First is creating a site-specific environmental program design, environmental monitoring program design. Your program design has to be site-specific, to be agreed on engineering terms and commercial terms, data confidentiality, regulatory adequateness, regulatory adequateness, developing your reporting standards in line with the national requirement. For example, in the UK, it's the Environment Agency, it's the ONR, it can be the NDA, but the IAEA is a good standard that I follow, and I'm meeting the client expectations. But there's one area where I think is quite a key challenge, which consultants have to meet and should meet all the time, and that is developing the land quality database with a GUI, GIS-based interface, so that gives the client managers access to their data and also gives the regulator the information that is needed. In terms of site-specific environmental monitoring program design, to be very careful in selecting what approach you would take to monitoring and how you would build the CSM. Generally would recommend have a thorough discussion with the regulator before deciding the GI design and how the CSM will be delineated, and also agree with the regulator what the program data management protocols will be. And now, obviously, the key challenge is the CSM characterization, and here several important steps that I encountered. Was data collection. We need an absolute representation of a site-specific time series data sets for all geoenvironmental typology data sets, ground gas, solvents, fractures, frequency of fractures, and even what's the site SOM or even the pH values. Complete site-specific time series data sets are quite important and make your life really easy. Understand and elucidate the structural geology of the site and its relationship with the land drainage and the built drainage, understanding the flow and transport and the lithology of the site, choosing the model very carefully. I've not named any specific model here, but choosing your FNT model and flow and transport model and projection models. For example, you're looking at a source depletion, then look at that very carefully. Hydrogeology, water balancing, and geochemistry, taking all these things into account. And how do you build your visualization? Traditionally, obviously, like everyone else, we've moved. Majority of the work was done in standard Excel packages and other packages, but we're trying to move away from that. Create a 3D visualization animation program. Run the visualization from a database based on Python scripts using regression equations for building the forecasting. And I have said AI interfaces. We'll talk about that later in the presentation. And finally, how do you integrate every line of evidence that you have in terms of porosity, flow field, fracture frequency at depth, and keep practicing building weighted lines of evidence to support the conceptual model that you have built. And the key is get the contaminant metrics right, particularly concentration and mass flux exchange that's taking place within the site and outside the site boundary. I picked up two examples for monitoring. DATQ is freely available, publicly available data sets, and so we'll, for the next few minutes, we'll discuss these two slides. So I looked at how environmental monitoring has historically been carried out at Hanford in the United States. It's one of the biggest nuclear sites in the world. And on your left, you should have a land management plan. On the right, you should have a land allocation plan. And essentially, all the monitoring that has happened on Hanford has led to the creation of land management plans and allocation plans. So if you don't know much about Hanford, then that is just about the whole Hanford site. But the most important characteristic of Hanford is this central plateau. It's about 75 square miles, and it contains all the waste tanks, millions of gallons of rad waste. And the key feature on the site, as you can see, is the famous Columbia River corridor. It's got a rad plume inside it, under it. And on your right is a slide which shows the land allocation plan, how environmental monitoring has essentially led the Department of Defense in the United States and the Department of Environment create it's a program they call CLOP. And that is based on all the monitoring data that they have collected. And they have a very advanced land quality database, flow and transport, and a GIS interface as well. As you can see, the area in the gray is where majority of the work it has taken place historically, and most of this area is now under conservation and preservation. And this has come about by really using some very advanced monitoring techniques. And they now have a new program on monitoring called the Altimus, which they run with BNNL and MIT. Okay, these are the plumes of Hanford. One is the left plume, which is the rad plume on 2001. That is that's an extract from the uncertainty analysis on the flow and transport model for the Hanford site. And as you can see, is quite a bit of iodine 129 there, and tritium, and this is plume right under the river Columbia. And on your right side is the most recent information that's available out there, or I could see. As you can see, there's GCE there. There is iodine 129. Again, not much has changed. The expected time of completing the remediation is 75 years. But I think they're going to be there for a long time. Again, shows how the power and versatility of the environmental monitoring data sets in land use allocation, in asset management, and environmental protection. It's a matter of national prestige as well, in my view. how good your sites are monitored and controlled. The second one is a Fukushima. Is quite a common. Any student who discusses who wants to know anything about nuclear land quality must study the Fukushima accident. Just briefly about Fukushima, what happened there was you had core meltdowns in 3 units, as you can see on your right screen. There's a picture of the 4 units, and you had radionuclides releasing into the reactor protective into the RPVs, fission products, noble gases moving into the primary containment vessel, condensing to form aerosols and directly getting released into the environment. The International Atomic Energy Agency's main hypothesis on this is on the IAEA website and the Fukushima website as well, and it clearly says there's a design leakage there, containment leakage, and essentially a subset of 3 failures: containment, design, and containment leakage failure. The amount of well, an interesting fact that I picked up was that the amount of noble gases released was exceeded the corresponding release from Chernobyl, actually. Particularly xenon 133, it's estimated that it was 1.5 to 2 times greater than Chernobyl. And on your right side is essentially the inset from the Fukushima. It's again from the IAEA's main report on the accident. And Fukushima is built on a sandstone aquifer, and that's a conceptual model, the direction of the flow of groundwater, and yeah, I think it's a good characterization carried out by IAEA. It's a good practice that sometimes I go back to refer to it when we're working, building my reports. Fukushima monitoring. The focus of the monitoring scientists at Fukushima has been on fishery harbors and ports, shallow water sediments, and fishing grounds. Looking at the regulatory setup in Japan, it's driven mainly by the Nuclear Regulation Authority and by different agencies of the Japanese government and by TEPCO as well. And the key isotopes that were monitored by this monitoring program was cesium and strontium and plutonium as well, and tritium, with cesium being key to understanding the biomagnification impact, particularly in the fish and in the food chain. I must say that Fukushima program, if we go back to that slide, it's come under some sort of criticism because of some of the monitoring practices adopted in some lessons that we can, particularly in TUSIT as well, we can learn from Hanford and Fukushima are that in the area, what I call what is the hydrogeological model, choose the FNT model based on new methods of characterization, it requires a new thinking, and data collection, build long-term data sets for your land quality database, which means you must have a database engineer with you. Conceptual site model and land quality database, experiences that you must drive the conceptual site model through the data and the land quality database and not outside it. Monitoring and hydrogeology, build your land quality database and the flow and transport model and the graphic user interface, and give client access to that and build that facility for the client. In terms of collaborations, key to the success of your project and key to the success of the program, build collaboration by competing and sharing knowledge with your regulator and with the client managers and with your modeling teams inside and outside your company. And as I said about Hanford, was recently at a hydrogeology conference, and I met one of the scientists who was heading one of the parts of Hanford's monitoring program. So they now use an Altimus, which is a fancy name for advanced long-term environmental monitoring systems. Essentially, they have covered the whole Hanford site in different sorts of sensors, and they have their built-in, they have the land quality database and flow and transport and the GeoEye. Obviously, it's a lot of expenditure, but depends upon the scale of the scrutiny that you're under from the regulator. I suppose that determines how advanced your monitoring design program should be, how advanced the objectives. The objectives of your program are entirely essentially determined by land use availability and by what the regulator wants. Environmental data management system, the EDMS, should be quite organized and agreed with the site owners. This is quite helpful for management of assets, and this is quite helpful to go through different phases of planning. It's quite helpful with infrastructure development, particularly with respect to sites that are going through, that are building new enrichment facilities, or planning to build enrichment facilities, or new build sites. Sorry, go back to that slide. Which means that once the old-fashioned style of having land quality professionals within the nuclear land quality team, it now needs a new approach. They should have a database consultant embedded within your team, so that you can meet the quality standards. Environmental monitoring. What are we doing here in based in Warrington and within Tilsid, and what's the vision going forward? This slide particularly shows you what are the key capabilities within our team, particularly with respect to these are capabilities that have developed over the last 2 years, with getting some focus, particularly in the last 12 months, looking at the design of the land quality database and GIS system, improving project management, ACFA testing, getting the K values as early as possible, building the GIS capability, working on the DVA capability for visualization and data management, providing the client with advice on nuclear land quality prioritization, so that they can apply for their planning permissions and prepare accordingly. And geochemical profiling of the site, and we have built this capability. And in some cases, we have an external pool of our experts who help us out. And ground investigation and design, that is quite a key capability we have. Fate and transport speciation, numerical modeling, characterization of waste, and the old-fashioned site investigation and characterization. So we do within our team in the business, we do a full life cycle. We can carry out a full life cycle of a nuclear site completely that meets the commercial and the regulatory objectives. What's briefly our vision for we position ourselves in the market is to be quite a prominent player in the nuclear market within UK and outside, and develop the approach to nuclear environmental monitoring. And this is constant research and training and education needed for everyone, for us within the team. And we also have within our wider business group scientists who help us develop new techniques of analyzing data and visualizing data, deploy quality resources and projects to meet the project objectives. A key target is to build electronic data management capability, and that's what the scientists I met at the Aerogeology conference bring some degree of artificial intelligence into what I call neural networks. When I say neural networks, that's fundamentally related to visualization of the data and forecasting of how the site will behave in the next 10, 15 years, particularly with respect to the source pathway receptor characterization and source depletion. And we endeavor to, with our experience, to provide our clients with land quality prioritization so that they can develop their databases and they can have land available for their whatever their activities, particularly in areas of reactor building or enrichment activity. In terms of technology and the market trend, where are we going? At this moment, we're focusing more on reducing the time that we spend in characterization. For that, the key is high resolution characterization. So we're moving, for example, I said in one of the slides, packet testing is I believe key when you have a site which has got, for example, fractures, and you believe that those fractures, along with the site drainage cover, is playing a key role in creating a regime of subsurface contamination, so that you can develop your remediation options. We're also looking at some other techniques like NMRs, different types of resistivity tomography, seismic refraction for building the 3D geological model. These techniques can be again, it can be time consuming to organize these operations, particularly on nuclear sites which need very specific approvals. So if you're choosing to do that, you have to get in quite early, and you have to balance what data you're going to get from these techniques against the traditional understanding of the structural geology of the site. And sometimes, quite often, I find that these techniques these techniques are adopted under the instruction of the regulators. Also, our aim is to keep building this key capability on land quality databases, particularly the flow and transport supported and run from the database, rather than just send a report over to the client, and supported by stoichiometry, influx measurement, and mass discharge measurements. In terms of market trend, I think environmental monitoring will play a key role in the nuclear, in the development and sustaining the nuclear activities right across Europe and in UK. I see nuclear as fundamental to greenhouse gas abatement in terms of its relationship with meet the challenges of climate change and sustainability. So it's got a great scope in environmental monitoring in promoting the nuclear industry, and dispelling some of the myths that are out there as well. Land management is needed for reactor and enrichment activities. There is a demand for that. In terms of market trends, I see that interfacing and collaboration with statutory bodies is becoming commercial arrangement. If the regulators are taking a lot of time to come back to you, we could go back to them and propose a different arrangement to create a more responsive architecture. For us, the major customers continue to be, it's not hidden, they're quite well known. Magnox and EDF and Sellafield, NTA, Urenco and BASE and ONR, and the Environment Agency as well. And I believe that the nuclear license sites will continue to have a significant spend on environmental monitoring activities and land quality management. That's going to continue, particularly with respect to, as I said, meeting the challenges of providing more clean energy and providing, and also the challenge of, in some cases, storing nuclear waste and disposing nuclear waste. To prepare this presentation, I just give you a quick, these are the references I used. And if I would recommend to particularly read the Fukushima accident technical volume, the description and the context accident. It's quite useful reference, and also go through, if you can, through the Fukushima database as well as the Hanford database. And I must point out this particular publication by Elizabeth Parker and John Cherry, which is the discrete fracture network. I use this paper quite regularly in terms of understanding the characterization and how to reduce the characterization loop on projects. I find this quite useful, and I believe it's an old piece of work, but it's quite useful. And that should be it. So if if you want to get in touch with us, please email us, or you can they will contact us. They'll send me an email, and I will respond. And also you could connect to us on LinkedIn. So if you have any questions at all, please, I'll be very happy to answer. I can see there's few. Okay. So we have, when do you go for a traditional approach and when for a two-sided approach? At what point do you decide, and how is that's in supply chain? The approaches of using the traditional as well as the other two-sided approach is depends upon fundamentally how complex the site drainage is working with. What's the relationship between site drainage, hydrogeology, what type of contaminants you are dealing with. My preference is to use two-sided approach, and that's based on several years of learning. And my background was from landfill gas monitoring, landfill monitoring as well. So in order to the two-sided approach has just not come about. It's as I said, I also pointed out this particular slide. I also pointed out to the publication from Parker and John and Jerry, and so it has come about, and it is prevailing, and it will mature in response to what the client's challenges are. This is purely in response to the commercial as well as to the regulatory challenges that the client has, and we do our best to meet those. And the second one, what is the land quality database and what are its key data typologies? Yes, as a land quality database is every data set that we collect, groundwater, logs, soil logs, photographs, all information gets organized in a relational database management system. Traditionally, this has been some people store in Excel or in Access, but my recommendation is use SQL service and connect that to your how to transfer, and make the client understand what are the benefits of it. The best two examples of land quality databases are, as I said, Hanford and Fukushima, particularly Hanford. It's got great rewards for the client, commercial rewards for the client, and can meet the regulatory challenges and plan their assets and plan their commercial operations. It does take time to build infrastructure around it, and particularly with respect to nuclear industry, it's a challenge to bring in new systems of work and new process. So, but in my experience, the clients are very responsive to new ideas, and they see the benefit immediately. Particularly, it gives them control over information, their own information. It gives them greater accessibility to their own information. And what's the role of artificial intelligence in environmental monitoring? Yes, recently it was discussed in the hydrogeological conference, and we believe it is going to be pivotal to the progress of environmental monitoring, particularly with respect to an example. The best example of that is the Altemis, which Hanford is running with MIT. They have several artificial intelligence experts on them using different advanced mathematical techniques. Some of them are quite new to me as well, and I see AI providing great help to the nuclear industry, particularly in the area of data visualization and forecasting.